Modern processors don't need to run at full speed all the time. In fact, smart software can significantly reduce power consumption by telling the CPU when to sleep and when to slow down. In this short video, we will explore two approaches to energy-efficient coding on ARM systems: bare metal power-saving instructions and operating system-level power management on Linux. Let's start with bare metal systems, where no operating system is present. ARM processors provide special low-power instructions that allow the CPU to enter a sleep state. One of the most important is called WFI, which stands for Wait for Interrupt. When the processor executes a WFI instruction, it immediately enters a low-power mode. The CPU remains asleep until an interrupt occurs. Once the interrupt is handled, execution resumes, and the processor can go right back to sleep again. This approach is commonly implemented using a simple idle loop, where the CPU waits, wakes briefly, and then sleeps again. However, there are an important requirement here. Interrupt handling and interrupt initialization must be implemented correctly. If no valid interrupt occurs, the processor may encounter an error that can even force a reboot. In addition to waiting for interrupts, ARM processors can also wait for events. For this purpose, the WFI instruction can be replaced by WFE instruction, which stands for Wait for Event. With VFE, the processor wakes up not only for interrupts, but also for events triggered by other CPU cores. Another core can generate such an event using the SEV instruction, which signals all cores at once. This mechanism is especially useful in multi-core systems where cores need to synchronize while consuming as little power as possible. Now let's switch to Linux-based systems, such as Raspberry Pi running Linux. In this environment, it's difficult to observe whether the CPU truly enters low-power sleep states. That's because the operating system constantly generates interrupts and events from hardware devices, communication interfaces, and interactions between CPU cores. Instead of relying on sleep instructions, Linux typically saves energy by reducing CPU frequency. This technique is known as dynamic voltage and frequency scaling, or DVFS. It's the same concept used in laptops and mobile devices to extend battery life. Linux exposes CPU frequency and power management controls through the CYSFS interface. For example, developers can write to files such as CPU frequency governor to control how the processor behaves. By setting the governor to power save, the operating system automatically lowers the CPU frequency and voltage. This reduces power consumption without requiring direct hardware control from the application. Even low-level programs written in assembly can interact with these settings using system calls. The operating system handles the actual power management safely and efficiently. In bare metal systems, power efficiency is achieved using instructions like WFE and WFI, combined with carefully implemented interrupt and event handling. In Linux systems, energy savings are typically achieved at the operating system level using CPU frequency scaling and system interfaces such as SYSFS. In both cases, the key idea is the same: let the processor rest wherever possible and only wake it when real work needs to be done.